Stripping down science. The Naked Scientists.
The Duchess of Cambridge's breasts will not be covered in the programme, but we do have an even more alluring offering for you this week. A full exposé, no less, on the world of robotics, because this week sees the first outing in Britain of the World Robotics Sailing Championships, which launch tomorrow in Cardiff. One of the organisers, Colin Salze, is here to talk us through the lineup. It is Sunday, September the 16th. My name is Chris Smith, and I am joined this week by Dominic Ford. Hello, Dominic.
Thanks, Chris. And we'll also find out how else robots are set to make an impact on our everyday lives in the coming years. And might they end up taking over the world, as in the film Terminator? Robotics professor Alan Winfield is with us to discuss the issue.
Plus, news this week that scientists have used stem cells to successfully restore hearing to deaf gerbils. That's coming up.
The Naked Scientists podcast is powered by UK Fast, the UK's best hosting provider. On the web at ukfast.co.uk.
Tomorrow, the 5th World Robotics Sailing Championships will be launched in Cardiff Bay, Wales. The event will see 5 teams from around the world pitting their robotic seafarer wits against one another in a variety of demanding challenges, from collision avoidance to long-distance sailing. Colin Salze is a robotics researcher at Aberystwyth University. He's also one of the organisers and a competitor in the championships, and he's with us from Cardiff. Colin, hello.
Hi.
So how did this competition get going?
Quite a few years ago, I was at the end of my undergraduate course and beginning a PhD looking in robotic sailing. And my PhD supervisor at the time was contacted by a guy from France called Yves Brière, who's a professor at a university in Toulouse. And they had this crazy plan to race robotic sailboats across the Atlantic. And so born out of that was something called the Microtransat Challenge. And the aim of that was that in 2008 we would sail with as many teams as were interested across the Atlantic. And in 2007 we planned to do a warm-up race off the coast of Aberystwyth. And in 2006 we did one in Toulouse. Almost simultaneously, a group in Canada actually started with the same idea, but on a slightly smaller scale, just racing 2-metre boats that were semi-remote control, semi-autonomous around, and they called that competition Sailbot. And when it got to 2008, we actually had some logistical issues getting the transatlantic race organised. So one of the teams who were competing from Austria, with a guy called Roland Stelzer at the Austrian Institute for Innovative Computer Science, founded what they called the World Robotic Sailing Championships, which was just to keep going this idea of having short, manageable races on lakes or just offshore where people could compete and sort of develop ideas and come together, and also to attach that with a one-day scientific conference on the whole robotic sailing field.
So the whole thing got together, and now you have an international community behind this endeavour.
Yes, I think there's about 20, 25 groups actively working on this worldwide, of which we have 5 or 6 here with us this week.
What are you actually working on? What are the challenges involved in making a boat sail itself?
So there's a huge sort of multidisciplinary set of challenges. The first is you've got to make something that floats, that will survive at sea, that will sail appropriately, that will be able to fight the currents. You've got to make a computer system that can sense the wind, sense where the boat's going, sense its direction, and actually compute a sensible course. And then you've got to build something electrical and mechanical that will allow you to set a rudder and sail appropriately and actually facilitate you sailing that. And all of that's got to work together, and it's got to work together for probably several months at a time if you're ever going to cross the Atlantic or stay out at sea to do oceanographic monitoring.
How big are the boats you're building?
So for the Microtransat, we've actually set a limit of 4 metres, mainly as a safety thing, that if they should collide with anything, they're not going to do too much damage. So at the competition this week, we actually have the smallest boats are 53 centimetres long, and they're off-the-shelf radio control boats called Micromagics. And we actually have 2 groups bringing them, and there's, I think, 7 of those in total. The largest boat with us this week is actually our own, which is called Beagle B, and that's 3.5 metres long and is based on a sailing dinghy that's actually designed for a disabled sailor.
So that's quite big, isn't it?
Yes.
So it's not just a question of making something float and then obey preset commands. This has got to do what really good yachtsmen and women do, reading the weather, reading the sea ahead, and reacting to change.
Yes, it does.
How do you program that?
Ours, we have a computer on board that reads from a GPS, a wind sensor and a compass. It has a set of waypoints that it tries to hit, and by evaluating those and setting the sail and rudder appropriately, it tries to hit them. More long-term, though, we have some sort of research aims as to try and start coping with things that fail and things that degrade, and how you might actually have to adjust the behaviour of the robot over time to cope with actuators that jam up, and maybe you can't move your sail as efficiently as you could before, or possibly you can't even sail certain courses. You have to adjust your course and think about different routes.
But what about other things like the tide? At different stages of the tide, not only will it run in a different direction, it will also run more fiercely or with less force. Can you sort of give it the charts and it will factor that in? Because obviously a person who is a human doing this would know, right, I'm going to face X number of knots of tide at a certain point, and so you'll compensate for that.
Yes, you can build in a tidal planner that tries to compensate for that. The difficulty with small boats is sometimes the tidal current will actually be stronger than you can make your boat sail.
Exactly, and a person would do something about that. They'd say, right, I have to come up with an alternative strategy, and they go the other way. The robot, what would that keep doing? Would it just keep on relentlessly trying to go the right way until it just ends up on the rocks?
Most of the robots at the moment would be that naive and just try and do that. It's an area of ongoing research, and there's certainly some people looking into trying to get around that one. But it's not a simple problem, especially when you get things more complex than the tides. You get tides combining with currents, combining with local conditions of the wind.
What about other boats? Because we have this international regulations for the prevention of collisions at sea that all people who get their RYA certificate and the international equivalents have to subscribe to a knowledge of, so we don't bash into each other, we pass to port and so on. How do robots react when they see another boat coming? How do they tell that is a boat in the distance, it's not a buoy, or it's a rock, or a lighthouse, or just a big wave?
Again, that's another ongoing problem. So there's quite a few approaches to that. One is that all commercial shipping carries a system called AIS, which is Automatic Identification System, that actually transmits a radio broadcast signalling their position. So one strategy is to pick up those broadcasts, but obviously that doesn't work for smaller boats that don't carry AIS. The other thing is to start looking with a camera or with some kind of radar to try and scan the horizon and work out where the obstacles are and try and avoid them that way. And also carrying basic things like navigation lights and radar reflectors so that other people see you and don't run you over, hopefully.
And is the idea of getting lots of people together internationally and introducing an aspect of competition, is that to sort of force the field forward a bit, or is it just for fun?
Well, both. It's for fun, but it's also, and it has made a huge difference in bringing the field forward. We started with 3 teams in 2006. We now have over 20 people, or 20 groups worldwide actively working on this.
And is this something that really will become an industry in future? Do we foresee a time when people will do away with Ella MacArthur and you just put a robot on the boat instead?
I think for actually sailing large passenger vessels, you'll always have a human in the loop just for a safety point of view. But what we might see is an increased amount of automation. But at the other end of the scale, what we envisage is that smaller boats might be deployed as oceanographic monitoring systems, or for monitoring coastlines with radar to look for smugglers, or maybe going and sailing long transects in waters you don't want to send people into, maybe in the Arctic or the Southern Ocean in winter. So that could really help with oceanography research and climate change research done without putting people at risk, and with something that's a bit more versatile than just drifting buoys that we tend to use at the moment.
And how far away are we from a situation where you can foresee a robot boat being able to do a circumnavigation?
Of the world? Or?
Yeah.
At least a few years away, I think, from that one. No one's made it across the Atlantic yet. We've had 3 teams try, ourselves in 2010, and a team from Brest in France tried both last year and this year. The team from Brest have done the best so far, and I think they got about 200 miles before they lost track of their boat. And actually, theirs washed up in Ireland a few weeks ago.
Oh, what, in one piece?
Mostly in one piece, fortunately.
So what went wrong?
They're not entirely sure yet. I don't know if they've actually got it back. It looked like something may have run over it, or a wave may have broken the rigging off, but the actual hull looked quite intact from the pictures I saw.
Thank you very much. Colin's with us for the rest of the programme. That's Colin Soze. He is a robotics researcher from Aberystwyth University. He's actually one of the organisers of the 5th World Robotic Sailing Championships, which are launching in Cardiff Bay in Wales from tomorrow. But later on in the programme, he's got with him US Navy engineer Professor Paul Miller, who also organises similar events like this in the past and is participating this year. We'll go back to them shortly to ask Paul a few more specifics about some of the things that they've been looking at.
Now, the word robot conjures images of shiny metal humanoids plucked from a rich history of science fiction. But until recently, real-world robots were found doing heavy work on production lines, often fenced off to protect people from harm. But now robots are increasingly coming out of those factories and into our houses. And to find out how they've made that transition, we're joined by Professor Alan Winfield from the University of the West of England in Bristol. Now, Alan, how far are robots from those science fiction depictions?
Well, I'm sorry to say, Dominic, some way away. It would be easy to be deceived because at present we can build some quite remarkably high-fidelity Android robots, especially if you look at some of the robots from Japan. But the problem is that their behaviour doesn't match their appearance. It's what I call the brain-body mismatch problem. So those Android robots may look terrific, but they're little smarter than a washing machine.
And I guess all of these robots are based on computers, and we've seen tremendous developments in those computers in the last 25 years. How has that affected what those robots are able to do?
Surprisingly little, and that may shock you. You're absolutely right that, of course, we have extraordinary levels of processing power, and we can put incredible computing power into the robots. The problem is, of course, that the computing power is just a raw material. It's how you use it that's important. And solving the fundamental problems of artificial intelligence, in particular general AI, the ability to solve general problems, for instance, still eludes us. So that's a problem of designing the AI. So until we solve that problem, no amount of computing power isn't going to help.
And I guess a factory is a fairly well-controlled environment where you know what kinds of objects the robot is going to encounter, whereas a home is a much more complicated place.
Well, that's exactly right. I mean, as you said in your introduction, Dominic, the transition that's going on right now is from robots in factories and warehouses and undersea exploration and so on, to personal robots, to robots that will actually be workplace assistants or companions, therapeutic robots in the home. But it's fair to say that we're still at the beginning of that transition.
I guess there are also safety issues here, because in a factory you can fence the robot off. But in a home, you really don't want it pulling someone's arm off.
Well, that's exactly right. I mean, one of the major problems that's being addressed in the field of human robotic interaction right now is robot safety. It's remains a very challenging and unsolved problem. And as you say, not just the physical, as it were, strength of the robot, but also the fact that the environment is completely unpredictable. And building a robot that can both deal with those uncertainties and be completely safe, utterly safe, around children, for instance, is a big challenge in robotics.
You mentioned safety around children. What sort of applications are you envisaging, and do these safety concerns affect your choice of applications?
Well, I mean, I mentioned children simply because children might be present in the home. Some people have spoken of robots that might, for instance, help, look after childcare robots. But personally, I think that's going too far. I'm one of those roboticists who think that some areas of human activity should not be replaced by robots, and I think childcare is one of them.
And I guess also looking after the elderly might be a similar problem.
Well, indeed, and care for the elderly is something that's particularly pressing in the Far East, and Japan and South Korea already are very advanced in healthcare assistant robots for the elderly. But I have to say that it's a problem that we're facing too in Europe. Again, very difficult technical challenges. But also the ethical questions are those that we need to be concerned about. I mean, in other words, would it be ethical to, for instance, replace a human carer with a robot?
What do you think about using robots in education? I guess there's two questions there, because there's whether they can be used to teach, and there's a question of whether children can learn about science and technology by playing with robots.
Absolutely. I think that the second of those points you just made is absolutely wonderful. And I mean, there's no doubt that robots are an extraordinary tool for education. I mean, in UWE, for instance, we've been using robots for probably 15 years to help to teach programming to undergraduate students. But as for robots actually being teachers, again, I can see roles for such robots as an assistant or offline teacher, but certainly not replacing human teachers. For young children, it'd be great if, their robo-teddy, for instance, might be able to read them stories, and that there's a kind of educational function in that.
So looking ahead, what do you expect to see in the future from robots in the next 10, 20 years?
That's a hard question. Certainly, there's a whole range of research that's going on right now in human-robot interaction. So, for instance, here in the lab, the Bristol Robotics Lab here in Bristol, so we have work, for instance, on gestural communication so that robots can understand human body language. We have research in object recognition and handling so that if you ask a robot, for instance, to pass you the cup of coffee, it can actually recognize the cup and then, of course, safely pass it to you. Other areas I think that are slightly more far out, but I think are equally important, are new materials. So robots need to be lighter, they need to be compliant and soft. Then, if all else fails and the robot falls on you, it won't do you any damage because it's too light, for instance. And then the area of robot self-awareness, for instance. I think that these future companion robots will have to have a level of self-awareness in order to function properly and do their job. And I think it's worth saying as well, Dominic, that putting together an enormous range of at the moment, separate pieces of robotics research is a grand challenge in robotics.
Thank you very much. That was Professor Alan Winfield from the University of the West of England in Bristol.
Alan, you going along to see Colin's boats?
Well, I'd like to very much. I know the group at Aberystwyth well, and terrific. Good luck with the race, guys.
I've had a question for you from Catherine Hiscox, and she says from Hemel Hempstead, will robots ever be able to think for themselves? What do you think?
Yeah, it's a good question. The problem is, of course, we don't actually know what thinking is. But I would say in principle, yes, they should be able to think for themselves. But it's going to be a long way into the future, I'm afraid.
Thanks very much, Alan. I was asking people on Facebook earlier, if you could have a robot, any robot of any description within reason, what would you have and what would it do? Lots of interesting suggestions coming in, including Martin at LH Collision, who says, one that serves me grapes. Another person who is Malgorzata Pupeka says, robots that can entertain my dogs while I'm away but would be cool and preferably organic so that they can smell and bond with the dog. You're listening to Dominic Ford and Chris Smith here with The Naked Scientist. This week we're talking about the studies of robots and robot races at sea, because it is a major event which is actually kicking off in Cardiff. It's the 5th World Robotics Sailing Championships, which actually launches tomorrow. We have lined up Paul Miller, who's a Professor of Naval Architecture at the United States Naval Academy, and he actually has with him Mariano Alvira, who is from Seascope in the US. They're both with us. Hello, you two.
Hello. Hello.
Paul, first to you. So why is the US Navy dabbling in this? What are you hoping to learn?
Well, the main reason we're doing this is as an application for our students to practice their skills that they developed during their undergraduate program. Naval architecture is designing ships and building ships, and it's really tough at the undergraduate level to actually build a whole ship. But at the smaller scale, just 2 meters long, our students can design, build, and operate the boat in their senior year.
I presume also, if you can get a robot to sail boats for you, it means that you wouldn't have to have expensive sailors aboard them. And that might be one reason why the US military is interested.
Well, one of the projects we've been looking at is as an oceanographic research platform. We've tested sending the boat out. The boats cost around $4,000 or $5,000 US, and it'll be able to go out and take depth soundings after a storm, for instance, to see how much silting has occurred. That would replace a vessel that may cost $10,000 or $15,000 a day to operate. So we're generating a lot of savings.
What are the big problems that you're struggling with in order to get boats that will do what Colin was saying earlier and come across the Atlantic? So you guys on the eastern seaboard in that beautiful city of Boston, where I know Mariano is from, he's going to talk to us shortly, so that you can come and see us here in England.
Our biggest problem so far has actually been power management. The boats, while they're powered by the sails, their computers and their servo controllers, for instance, for the rudder and the winch that controls the sail, do require electricity, but the boats only weigh about 40 pounds, and there may be only room for a few pounds of batteries. So how do we generate that power in all weather conditions to maintain that computer operation?
But batteries have come a long way, and being out under the sun every day, you must be able to get quite a bit of energy from solar or maybe even wind.
We can get some solar power, and we're hoping that will be enough, but actually the trade-off is that if you made the boat big enough to carry a lot of solar panels, it would actually become too heavy and slow. So we're concentrating on a fast, small boat that would have very small solar powers and maybe a small wind generator in order to produce the power. But like any other wind-driven device, you need wind to make it work.
Let's switch to Mariano Alvira, who is from Seascope in the US. You've come over also for the Robotic Boat Racing Championship. What are you entering, Mariano?
We are entering 2 boats. The first is a smaller half-meter boat that's a kit class, and then the second boat is a 1-meter boat, which is entirely custom-made.
Unlike Paul and Colin, who are both affiliated to professional organisations or universities and so on, you are doing this as a hobby.
Yes, it's myself and my girlfriend Taylor. We do this for fun.
So what are the things that you're working on with your boat? Is it just literally staying in the race, or are you hoping to win?
Our biggest problem is primarily boat issues. We're not boat designers. We're not very experienced in that, but we're very good with electrical things and mechanical things and software in general. So, for instance, last year, one of our boats sank right before the contest, and, we've learned since then how to make boats not sink, which is sort of a big deal.
That kind of matters, doesn't it?
Yeah, it turns out to be pretty important.
And Paul, so will you be keeping an eye on what Mariano's up to? And if it looks promising, then the Navy will nick it?
Probably.
Excellent.
You must have quite a lot of sort of translation going on here between what people like Mariano come up with, the kind of work you do for fun, but then also you see potential and you could translate that back into industry and also into what the Navy needs to do.
Absolutely. The beauty of these competitions is by interacting with the engineers and scientists from around the world, not only do we learn different techniques for making these boats work, but we also establish great relationships with the other people. But some of these very clever ideas that folks have come up with, I bring back to the classroom, and then my students benefit from that wider range of thinking. And some of those applications may end up benefiting the Navy in the future.
So tell us about the vessels that you're putting into the race, and what are the odds of you winning?
Well, the boats that we have are all completely designed and built and operated by our undergraduate students. And each year they'll do a whole new boat design. So we're on now our 5th generation boat, although the one we brought to this competition is our older 3rd generation boat. What we found is that when it is actually working, it is quite fast. The downside is it doesn't always work. There are those pesky electronic devices inside that once they get wet, they just don't like to work.
Oh dear. I mean, that's pretty fundamental. Boats go near water.
Yes, it is.
So what can you do?
Well, we try very hard to make the boats watertight. Actually, one of our tests is we take the boat and we submerge it underwater for 2 days. And theoretically, the boat then comes up dry. And this boat has passed that test numerous times, but every time we go in and work on it, there's a chance that one of those seals doesn't work anymore, and we may get another leak.
So is it quite literally that you've got little motors and things which are winding all the sails in and that kind of thing? Is that how they're actually working? And if so, how do you keep that dry?
In fact, that is the case on this 3rd generation boat. Our later boats use a servo-hydraulic type system, which is much more watertight and more reliable, but does draw more power. On these earlier boats, they actually are using model scale robotic sailing devices, servos, and they do come through the deck, and so there is a watertight seal at that deck that a winch drum, for instance, goes through. And in one case, we actually use balloons as the seal.
We'll find out more in just a second. Paul, thank you very much. We were listening there to Professor Paul Miller, Professor of Naval Architecture at the United States Naval Academy, and he was also joined by Mariano Alvira, who's from Seascope in the USA. He is a hobbyist who's entering this robotic boat race.
From protons to photons and gluons to muons, The Naked Scientists. Science that's fundamentally more fun.
Now, you're listening to The Naked Scientists with Chris Smith and with Dominic Ford. We'll return to our topic of smart sailing robots shortly, but first let's take a look at some of the stories that have been making headlines around the world, scientifically speaking, this week. Dominic, I've got a quick question for you. What would happen if you were to drop a ball bearing about 2 centimetres across that was at 400 degrees C into some water?
Well, I guess when that ball bearing makes contact with the water can get incredibly hot, and so I guess it would boil around that ball bearing.
OK, now let me throw in an added twist. What would happen if I first coated the ball bearing in a substance known as a superhydrophobic layer? In other words, something that was extremely good at repelling water.
So I guess the water can be repelled away from that ball bearing, so it might not be in contact. But surely some of it would still be touching the ball bearing and still boil. Well,
a group of researchers have done the experiment this week and got a very interesting result. I'll tell you in a minute what actually happened. Other news first, though. An interesting way to repair and restore hearing has been announced this week. Marcello Rivolta, who's a researcher at Sheffield University, has published a paper in Nature where he and his colleagues have found out how to persuade human embryonic stem cells to turn into the kinds of cells that produce the hair cells in your ears that turn sound waves into nerve signals, and then also the nerve cells that transmit those electrical signals from the hair cells into the brain to restore hearing, because a subset of people who go deaf are deaf because they've lost those nerve connections. So if we can put them back, then we would potentially restore hearing to these individuals. The discovery centres on the fact that if you take cells from a certain part of the developing embryo and you expose them to two growth factors, FGF3 and FGF10 are the names of those growth factors, then it drives the cells to be fooled into thinking that they're in the ear part of the developing embryo, and they turn into these stem cells that are going to produce the hair cells and the neurons. And they've identified some markers that these cells turn on that can be used to identify what those cells are. They're called PAX2, Nestin 6-1 and GATA3. Those are the markers that the cells make. And they can pinpoint clusters of cells that are going to make these nerve cells. So they identified those, isolated them and cultured them in a dish. And then they took some gerbils that had a drug-induced form of hearing loss, and they injected these nerve stem cells into the cochlea, which is the inner ear where the nerve signals originate from for hearing. And after about 6 weeks, they all got hearing recovery, but in some they got complete restoration of their hearing. When they looked in the brains, they found labelled nerve cells showing that these nerves had regenerated the connections into the brain, thus restoring the hearing in these animals. And they say the ability to reinstate auditory neuron functionality paves the way for a future cell-based treatment for auditory neuropathies. And they go on to say it may also, in combination with a cochlear implant, these electrical devices, offer a therapeutic solution to a wider range of patients that currently remain without viable treatment.
So is this now likely to go into clinical trials in humans?
Well, one has to be cautious because it involves embryonic stem cells, and we have to make sure when using any kind of stem cell that they are safe. But the proof of principle is the key thing, and this is an amazing step forward because it means we could basically take a range of disorders which are very hard to treat at the moment and restore near normal hearing if this goes the same way in people as it has in these animals with this technique.
Sounds good to me. Now, moving from ears to supernovae. A paper published this week in the Astrophysical Journal suggests that up to 90% of supernova explosions go unseen by the surveys designed to look for them. Now, supernova explosions, of course, happen at the ends of the lives of very massive stars. They happen when these stars run out of fuel, when their cores collapse, when there's a tremendous release of gravitational energy from that gravitational collapse, and that blows off the envelope of these stars with tremendous violence so that they can outshine billions of more normal stars for a period of a couple of weeks. But if you actually go out and look for these events, you find they seem to be quite rare, even though predictions are that they happen every 20 or 30 years in a galaxy like our own Milky Way.
So why are they rare then?
Well, it seems that these events are happening preferentially in areas of the galaxy where we don't have clear lines of sight, because there's a material in space called dust. Now, this is basically soot, which is produced in the envelopes of stars. It is basically soot from the burning process, and it pervades the space around those stars. And if you have too much soot, you would basically have a smoke screen, and you can't see through it. So what a team led by Sepio Matilla of the University of Turku has done in a paper in the Astrophysical Journal this week is to look at nearby galaxies using infrared telescopes, which can basically see through these smoke screens of dust, and compare what they saw with what surveys using more conventional telescopes had seen. And what they found was they saw a tremendous number of supernova explosions in these very dusty, sooty parts of the galaxy, where you wouldn't be able to see those supernova explosions with optical telescopes. So they think that up to 80 or 90% of the supernovae are happening in these very dense parts of the galaxies where you simply can't see them.
Extraordinary stuff. Dominic, thank you very much. Well, also this week, Cambridge University scientist Beverly Glover has discovered what she says is the brightest thing, talking of supernovae, in nature, here on Earth. And guess what? It isn't Stephen Hawking.
What we've found is that the fruit of a plant called Pollia condensata that lives in Africa is the brightest thing in nature. It reflects a higher percentage of the light shining on it than anything else ever recorded, including the famously bright, shiny butterflies that you see out there. So it's a blue-coloured fruit with speckles of pink and yellow and green in it. It's iridescent. It changes colour as you look at it from different angles, and the colour is really bright and really striking.
How did you find it?
A colleague in the Royal Botanic Gardens at Kew was looking through their collection, and she knew that I was interested in plants that use structures to generate interesting colour effects, so not just your usual pigmentation, but more unusual or striking colours. And she saw these very bright blue fruits that had been collected over 50 years ago. Even though they'd been pressed and dried, they were still as bright as when they'd been collected. So she passed them along to us to do the analysis.
And how do you know that they are the brightest thing in nature?
Well, they may not be. They're the brightest thing measured so far in nature, is a fairer way to put it. So the percentage of light that they reflect back is higher than that reported for anything else that anybody's ever measured.
Do we know how they do that?
Yes, we do. It's a very clever mechanism, and interestingly, it's an example of convergent evolution because a lot of animals use a similar mechanism. If you think of bright blue butterflies or beetles, then they're highly reflective because they have layers of secreted chitin on top of their wings, and the layers are spaced at just the right frequency to reflect back particular wavelengths of light. And the cleverness in the system is that the more layers you have, the more light you reflect back, so you get a higher percentage reflectivity. What our fruit is doing is that every individual cell on the outer layer of the fruit has layers within its cell wall. So these are plant cells, they have cellulose cell walls, and those walls are made up of layers of cellulose, and there are many, many, many layers of cellulose, and so of course they're able to reflect a very high amount of light back.
Why do they do this?
Well, we haven't done any experiments out there in the field to check this, but their distribution suggests that they're dispersed by birds. They don't pop open of their own accord, so they probably need to be swallowed or to go through the bird's digestive tract for the seeds to come out. And yet they don't provide any food reward. And so we think that it's actually a trick, that nature's come up with a cunning scheme for attracting birds by being just really bright and shiny, even though there's nothing in it for them, really.
Would that be birds that like shiny things like magpies and bowerbirds that like to decorate their nests with bright things to attract females?
That's very likely. It could also be that they just look like really bright blue juicy fruit, but you'd think a bird would learn that quite quickly. So we think it's more likely that it's about birds that decorate their nests and are trying to attract females.
And given that you've worked out how the fruit does this, could we do anything similar, or could we use that knowledge to produce ultra bright things for us to use?
Absolutely. So it's a very nice setup because it's doing it with cellulose, and cellulose of course is highly biodegradable but also extremely cheap to grow because plants are basically made out of it. So if we can figure out how the cellulose is organised in that way, we could potentially grow food colourants which are entirely non-toxic, biodegradable, or colours for fabric as well. So there's lots of potential application there.
But would they be like the Henry Ford? Would they be any colour you like as long as it's blue?
No, not at all. The stacking frequency of the multi-layers determines what colour you get. So the fruit is actually multicoloured because although most of the cells have their cell walls stacked at a frequency that generates blue, some are stacked at a slightly wider spacing and they generate yellow or pink or red.
Brilliant. Sorry about the pun. That was Cambridge scientist Beverly Glover discussing the bright blue fruit of the Pollia condensata plant. That was work she published this week in the journal PNAS. Now back to the ball bearing story that I tantalised you with earlier. So we drop in a super hydrophobic coated steel ball bearing at 400 degrees. What happens? Well, in the words of Nilesh Batankar, who's a researcher at Northwestern University and has published this in the journal Nature this week, he said it did nothing. Actually, this is really interesting because they were using very fast frame video footage of what happens when you do these experiments because they were intrigued by what would happen if you keep the water away from the surface of the ball. And the reason it does nothing is because the ball immediately causes a pocket or an envelope of water vapour to form around it, and the super hydrophobic water-repelling surface on the ball they coated it with keeps the water away, whereas the vapour can get very close to the surface because it's not repelled in the same way. So it acts like a buffer. And it keeps the water away. The water, therefore, cannot boil off on the surface, and the ball just cools down gently by the vapour, conveying heat from the ball surface into the surrounding water. Why is this important? Well, apart from being a good party trick, if you're equipped to do it, it also could have industrial applications because this whole business of when you drop water onto a very hot surface and it immediately fizzing and skittering around, as it's known. That's called the Leidenfrost effect, after the German man who first described it, actually in the 1700s. This is bad industrially. You want to be able to heat things up in thin films and gently evaporate them off without having them skittering around all over the place. So it could have industrial applications as well. But did you get it right? Answer no. You had to think about it for a while.
Well, it's incredible to have a scientific paper where the results were that absolutely nothing happened.
Now, Facebook. Nearly 1 billion of us use it. But does it affect how we make important decisions? James Fowler at the University of California, San Diego, has been looking at the social networking site Facebook and how it can influence voting behaviour. Now, James, hello, welcome to the show.
Oh, thank you.
You famously showed that if people have overweight friends on Facebook, then they're more likely to put on weight themselves. But now you're turning to politics.
Yes, we are. And this week we reported the results of an experiment that we conducted on Election Day in the United States in 2010, where we randomly assigned to get out the vote messages to 61 million people on Facebook. There were two different kinds of messages, one with faces of friends and one without, and there was also a control group that received no messages. And the results of the experiment showed that the message directly mobilized 60,000 people who saw the message, but it also mobilized an additional 280,000 people who were friends of the people who saw the message. And we were able to do this because in the United States, public voting records are public, and we were able to match about 6 million of the Facebook users to publicly available records to see whether or not they actually got to the polls.
Oh, so you could check up on them as well. So just to recap, you had 3 groups of people, a control group who you just looked at and just monitored their behaviour. You've got a group who get a little button which says go and vote, and another group that say go and vote, and by the way, here are some friends of yours who voted.
That's correct. And the interesting thing about the two different kinds of messages we showed people, though, there was one that had pictures of their friends who had clicked on the button during the day, and another one didn't have these same pictures. And what we found was that the one that had the pictures actually was the one that did all the work. The one without the pictures, the rate of voting for the people who got that message was exactly the same as for the people who saw no message whatsoever. And so these pictures of your friends are what seem to be doing most of the heavy lifting in terms of the total effect of the experiment on real-world behavior.
But do you know, James, whether it is just seeing pictures of your friends that makes you attend to that bit of the screen more and for longer, so you notice the go and vote now message more? Or is it that the friends have voted and this makes you think, wow, I'd better keep up with what my friends are doing?
That's a good question, and we would like to figure this out, I think, in a future experiment. Right now, we just know that the message worked, but it's possible that it's just something that draws your eyes to the message because, just like when you see a list of random words, if your name happens to be in that list of random words, you're likely to be able to pick it out very quickly. Seeing faces of friends, it might cause you to attend the message. But one of the things that we were able to show was that not only was it the case that people who saw faces of their friends voted more, but the friends of the people who received the message voted more. And so the consequence, there was something that happened on the way from you getting the message to your friend voting that probably had something more to do than just attending the message. It had to do with a process of social influence.
So what are the implications then? You put this message up and people see that their friends have reacted to it, and you end up with a bigger result through the social networking impact than the primary advertising in the first place. Facebook must be delighted.
Right. Yeah, no, it was really interesting. To make it just perfectly clear, for every one person whose behavior was changed directly, there were 4 friends whose behavior was changed. And the interesting thing is I think that campaigns, they've gotten very smart in the last few years in countries like the United States and in Europe, and they do experiments. They do these message testing on a large scale, but I think that they don't necessarily utilize all this new social network information that we have. And what this really shows is that if you were just looking at the people who receive the message, you'd be missing the whole story. The network is really key here.
Is the fact that voting is something that people should universally do also important? Because if you had conversely put up an advert saying Mrs. Whoever bought a Ferrari, now that's only going to be relevant to a subset of people and a subset of friends, and therefore is unlikely to have the same impact as if it said go and vote, because that's something that doesn't attract a physical cost and also is something everyone should do.
I think that's exactly right. And in particular, I would expect these social effects to be stronger for things that we think of as social behavior or as socially appropriate behavior. Another thing that we found in the study, just like we have found in other studies, is that there are some people who clicked on the button in this case, but then we went to check up on them, they didn't actually vote. And I think one of the reasons why is because it's highly socially desirable to be seen as participating in politics. When it comes to buying a Ferrari, you might get some social benefits out of owning a Ferrari, but there's not a lot of people saying, well, you have to vote, this is your obligation, to own a Ferrari. So I do think that it may be the case that we wouldn't see the same strength of effects for other kinds of things online.
What's worrying me, though, is the sorts of numbers that you're producing from this study of people whose voting behaviour was influenced. If you look in the state of Florida in the Bush-Gore election, that was won with nearly 600 votes only, a tiny number. You're influencing orders of magnitude more people with this study. So does this mean that potentially a savvy politician using Facebook could actually totally skew an election result then?
I do think that these are going to be effective tools, but everyone is going to know about them. And so I think that what you'll see is both sides trying to use the tools and both sides trying to mobilize their voters. And it's important to remember that although it was a fairly large number of people, 340,000 people, this is out of 61 million. And so it's a small effect, but because it's spread out over a very, very large number of people in a very, very large network, I do think it's possible that as we learn more about how these processes work, that you could do targeting and you could get those 537 voters in Florida that you would have needed to change the outcome of the election.
James, we'll have to leave it there, but thank you very much. That's James Fowler from the University of California, San Diego, and he published that work this week in the journal Nature. Dominic.
Now, with a roundup of what else has been hitting the scientific headlines this week, here's Martha Henriques.
Eating a high-fat diet during pregnancy could increase the risk of breast cancer of mothers, their daughters, and even their granddaughters. Sonia de Assis and her team at Georgetown University compared two groups of pregnant rats. One fed a high-fat diet and the other fed a normal diet. 3 generations of DNA are present in a pregnant mother: her own DNA, the DNA of the daughter in her womb, and the DNA of her daughter's eggs, which are already present in the developing fetus. The high-fat group of mothers showed increased estrogen levels, which were linked to cancer-causing chemical changes to DNA of all 3 generations. This study, published in Nature Communications, will help scientists understand how breast cancers are inherited.
The important message here is that ancestral exposures, what your parents or grandparents were exposed to, can affect your risk of disease, and in this case, breast cancer risk.
Rain is more likely to fall over dry ground than wet ground, a study published in Nature shows. Christopher Taylor and his team at the Centre for Ecology and Hydrology looked at images from weather satellites around the world to track where storms happen and compared this data with measurements of local soil wetness. Previously, it was thought that the high humidity over wet ground would be more likely to seed storms. But Taylor found that the reverse is true, and the higher temperatures over drier ground is a key factor in creating storms. This, say the scientists, pours cold water on current weather forecasting and climate prediction models.
Rather surprisingly, we found that the models do the wrong thing in the sense that they produce rain over wetter soils rather than drier soils. That's quite an important problem for the simulation of droughts and also for weather forecasts. And it's one which I think weather centres really need to start thinking about how they represent that process.
Scientists have found 5 genes linked to facial appearance. Manfred Kayser and his colleagues at the Erasmus MC University Medical Centre in Rotterdam used MRI images from thousands of people of European descent to map 48 key facial characteristics. The genome sequences of over 4,000 people were then combed for genetic hotspots reproducibly associated with these facial landmarks, identifying regions on chromosomes 1, 3, 5 and 10. While 3 regions had been identified in previous studies, 2 were entirely new. Kayser hopes that further work building on this study, published in PLOS Genetics, will lead to advances in forensic science.
You could imagine that at some point one will be able to predict facial appearance, facial shape from a DNA sample. So in other words, you take a DNA sample, you do your genetic analysis, and you come up with a facial image.
And finally, a Boeing 747 with a difference will be lifting off this November. SOFIA, the Stratospheric Observatory for Infrared Astronomy, will be carrying a telescope with a diameter of 2.5 metres and will fly at 40,000 feet into the stratosphere to view the universe in the infrared. At this height, SOFIA will be free of the cloud layer that blocks infrared light from the ground. Eric Young is SOFIA's Science Mission Operations Director.
We'll be looking at the cooler things in the universe, such as planets, dust clouds, star formation regions, and external galaxies that give off most of their radiation in the infrared and which are too cool to give off light at visible wavelengths. By doing this, we're able to have a much richer view of the universe.
Eric Young, ending that report from our Naked Scientist newsflash with Martha Henricus. And the references for that and all of our news this week can be found online at thenakedscientist.com/news. Global warming may dominate today's environmental headlines, but not so long ago it was acid rain. Caused primarily by emissions of sulphur dioxide and nitrogen oxides from power stations and factories, these oxides form acids that acidify soil, damage plants, and end up in our river systems. Acid rain emerged after the growth of industry, and although the problem peaked in the late 1970s and early 1980s and has largely gone away, at least in Western Europe, its legacy lives on. Planet Earth podcast presenter Richard Hollingham talked to Steve Ormerod, Professor of Ecology at Cardiff University, about the issue and began by asking him about the long-term effects of acid rain.
About half of the length of rivers in upland Wales, that's about 12,000 kilometres overall, have been affected by the problem of acid rain. And what we've been trying to understand, essentially, is the recovery processes that have occurred in our river system, particularly with respect to effects on organisms that live in the river, insects, fish, and then consequences also for things like river birds.
And how have they recovered, or haven't they?
As you would expect, as emissions of acidifying substances have gone down, so the river pHs have slowly come up, something like about 0.2 to 0.3 units every decade. But what intriguingly we're seeing is that there is a mismatch in the speed of recovery in chemical terms, and that actually shown by the organisms that live in rivers. And what we think is that the ecological and biological recovery is lagging behind what you would expect from the change in chemistry.
So the river water is fine and it should support much more life than it does?
The river water, in fact, is fine on average. What we think is the reason why organisms aren't recovering quite so rapidly is that during wet conditions, stormy conditions, exactly of the type that we had this summer, there is a re-acidification, so short duration episodes of acidity that wipe out acid-sensitive organisms, and we think that's what's preventing this longer-term recovery.
Where's this acid coming from? Why are you getting these short bursts of acidity?
Even just adding lots of water to our catchments by the way of rainfall is enough to dilute all the calcium and magnesium that would normally buffer acidification, and also because of that kind of 150 years of the stored effects of acid deposition, of acid rain, we've very substantially depleted what buffering there might once have been in our soils.
How does this compare to ocean acidification?
So these really are two extremely different but quite interesting processes. So in the case of river acidification, it's sulphur and nitrogen oxides that are responsible for the acidifying substances. In the case of marine systems, essentially a pH reduction is being caused by huge volumes of carbon dioxide that are dissolving in seawater and actually driving the pH down. What's astonishing is how different the pH reduction is. So in the case of marine acidification, we're talking about 0.2 or 0.3 of a pH unit. In rivers, acidification that we saw because of acid rain was something of the order of 1.5 pH units, so dramatically different.
Well, the reason that the oceans are becoming more acidic is because of increased carbon dioxide in the atmosphere. And I'm also with Matthew Dray, and you're looking at what the increased effects of carbon dioxide in the atmosphere might have on freshwater.
That's right. So my work involves looking at how elevated atmospheric carbon dioxide affects tree leaf litter chemistry, and then how that leaf litter then decomposes in freshwater ecosystems. So what we're looking at here is that increased carbon dioxide affects leaf litter by changing the composition of its carbon-nitrogen ratio. And when the carbon-nitrogen ratio decreases, we see effects on the river system.
So the chemistry of leaves is changing.
That's right. Basically, we end up with carbon levels staying the same, but nitrogen levels dropping relative to that carbon. Now, what happens alongside that is that we can get other changes. That includes increases in defensive chemicals, which generally are quite unpalatable to organisms that might feed on that material. We can also see increases in things like what are called lignin and cellulose, which are basically the structural components of those leaves. So therefore, carbon dioxide makes those leaves tougher and more difficult to break down.
So why does this matter for the river?
Rivers in woodlands are very dependent on inputs of leaf litter. That's the main source of organic nutrients. When that changes, when the amount of carbon changes, you then find that the general chemical composition of that river will change at that point and further beyond that point downstream.
Steve Ormerod and Matthew Dray from Cardiff University on how the atmosphere affects our rivers and streams. And a longer version of that report from Richard Hollingham can be heard on our Planet Earth podcast. There's a link on our website, or you can find it via Planet Earth online.
And this is The Naked Scientists. Chris Smith and Dominic Ford with you. And our guests this week are robotics specialists Colin Sauzet, Alan Winfield and Paul Miller. And we also have sitting in the wings amateur roboticist, I suppose you could say, Mariano Alvera from Seascope in the USA. I asked you earlier if you could tell us what you would like to have in the way of a robot, if you could have any kind of robot. Lots of these coming in. Kevin Norman says, telepresence robot to commute and go to work and attend meetings for me. God, wouldn't we all like one of those? Mohammed Mirza says, my prediction, lifestyle in the future will be like a surrogate, an iRobot movie. And that's probably a very good place to start because, Alan, one of the things you touched on with Dominic was this whole issue of safety. Are we going to see iRobots in the future? Are we going to see the future where we could have the Earth taken from us?
No, I don't think so. I suppose, to put it very simply, why would we engineer robots to take over the world?
That's a very good question. I guess we wouldn't, but then if they become clever enough to start writing their own future, I suppose they could. Here's Catherine. She's on the line in Hemel Hempstead. Hello, Catherine.
Hello.
What can we do for you?
I'd just like to ask, what exactly is robotic mapping and how does it work?
Can you elaborate for us, Catherine?
I looked on the internet and apparently it's where robots are able to actually map out the area that they're in. You know, they can tell where they are when they hit a wall, etc.
I think you're referring to something called simultaneous localization and mapping, sometimes called SLAM. And it's an amazing technique where robots can estimate their position and both localize and, if you like, build a map of the environment that they're in at the very same time.
Alan, thank you. A question for the sailing guys. Can the same developments, we're wondering, be applied to submarines, or is attenuation of radio in water a big problem? What do you lot think? Colin, are you there, or maybe Paul could talk about that?
Attenuation of radio in water is certainly a problem, but a lot of the control theory that goes into making a surface boat work can also apply in the submarine, and certainly the issues of getting things waterproof is even harder in a submarine because you've got added water pressure. And actually a few of the groups who are here actually also into submarine stuff.
What do you guys think? Paul?
Absolutely. I think that field in many ways is more advanced than the robotic sailing because you've got that somewhat simpler case of you're under power, and so you don't have to worry about what the wind is going to do to you.
One here for Alan, which is Matthias Tula, says, what are the latest advances in telemedicine? I suppose this is important too, isn't it, Alan? Healthcare at a distance.
Yeah, absolutely. The Da Vinci robot is already quite well known. So if for instance, you have a prostate operation, that's likely to be using a teleoperated robot to do the internal surgery. And it's a field that's moving very fast indeed.
Alan, thank you very much. Well, we're actually very short of time, so we'll have to draw it to a close. But thank you to our guests with us this week for answering all those questions on robots. Dominic.
Now, searching for the origins of life, here's Hannah Critchlow with our question of the week.
The Naked Scientist's Question of the Week, brought to you in association with the How to Wisman Foundation, supporting science and education from Alpha to Omega.
This week, we question life on Earth.
Hi, this is Beryl Wary calling from Richmond, Virginia. I was wondering, if Earth is such a great place to live, why to our knowledge has life only begun once on this planet? Why don't we see new life beginning here every day?
First up, let's define what life on Earth, as we know it, actually is, by asking Dr. Nick Lane, lecturer in genetics, evolution and environment, at University College London.
All life as we know it on Earth is composed of cells with an enclosing membrane, DNA as the hereditary material encoding proteins and so on. all cells share a lot of their basic biochemistry, right down to the same genetic code, the same ways of making proteins, even the same ways of generating energy.
So, given that, has life as we know it, or indeed alternative forms of life, arisen more than once on Earth?
We don't know for sure that life only started once on Earth. All we know is that all the living organisms we've ever looked at are plainly related and so almost certainly derive from a single common ancestor. If life arose repeatedly, then all other separate origins must have disappeared without trace, perhaps outcompeted to extinction very early on by the more successful cells. The fossil record of bacterial cells goes back about 3,500 million years, that's 3.5 billion years, and so far as we can tell, these cells were very similar to their modern equivalents.
So different forms of life may have started, but it seems that just our form of life survived over the last 3.5 billion years. And where could our type of life have started?
Deep ocean hydrothermal vents are the systems most likely to have given rise to life. These far from equilibrium systems do at least favour the production of organic molecules, the biomass that makes up cells. But the level of self-organisation and dynamism required to get from cell matter to living cells is so great that we're in no position to specify the probability of life arising even in the most favourable environment.
So, if we're told that conditions on Earth are so suitable for forming life, then why aren't new types of life arising all the time on present-day Earth?
There are two big differences today, which mean that life is almost certainly not continuing to arise even in these favourable settings. One is the chemistry of the oceans. 4 billion years ago there was no oxygen and much higher CO2 levels, which together are much more conducive to life. And then secondly, today's vent systems are already packed with living cells, which are far more effective at converting raw materials such as hydrogen and CO2 into biomass than any primitive prebiotic system could be. So, however likely life might have been at the beginning, it's extremely unlikely that life could originate again on Earth today.
So, David, it appears that life may have arisen a number of times on Earth, but the most successful form of life, using organic biochemistry as we know it, proliferated and has been so successful that we've altered the environment simply by being here, and thereby made it less hospitable for other forms of life to initiate. Well, that's left me feeling rather special, and with that question fully evolved, we expend brain energy to ponder the next one just in.
So my name's Gary Lester from Buckinghamshire, and my question is, can I think myself thin? So can I eat a really large pudding and instead of hitting the treadmill, do a math problem instead?
What do you think? You can tweet at Naked Scientists, write on our Facebook page, email chris@thenakedscientists.com, or join in the debate on our forum, which is at nakedscientists.com/forum.
Hannah Critchlow.
I've been trying that trick for a very long time, Dominic. I'm doing enormous numbers of problems after all the puddings. It's not working. That is it, I'm afraid, for this week. We actually run out of time. Next week, we're taking on your science questions, so do please send them in. We need very good, wacky questions. The wackier, the better, in fact. You can send them to chris@thenakedscientist.com. You can also tweet at Naked Scientist or paste them to our Facebook page, facebook.com/thenakedscientist. But just before we go, and before I say thank you to our wonderful guests this week, I have a very big favour to ask you. It's 2 years since we last ran our Naked Scientists audience survey, and this is where we take a very close look at everything that we do, and we also ask you to take a look at what we do and tell us what you think about it. It's worth doing this because we are incentivising you with 10 quid's worth of Amazon vouchers to the first 10 people out of the hat who have responded to the survey by 12/12/12. There's a memorable date for you. You can find the survey at nakedscientists.com/survey. Fill it in and tell us what you think and what you would like us to do more or less of. Meanwhile, thank you very much to Colin Soze from the University of Wales in Aberystwyth, Alan Winfield from UWE, Paul Miller from the US Naval Academy, and our production team, Hannah Critchlow, Tom Simpkins, Martha Henriques, Alan Boyd, and Ben Vousler. Until next time, thanks for listening and goodbye.
The Naked Scientists podcast comes to you from Cambridge University and is supported by the Wellcome Trust, the EPSRC, the STFC, the Natural Environment Research Council, and UK FAST. For more cutting-edge science, join us online at nakedscientists.com.